I welcome you back to this 25th of December tutorial, the Christmas edition of Formulae, Stoichiometry and Mole concept.
Christmas, little Christmas, omwaka moja, leka kube kwasanye.
So we had looked at Roman 1 and then Roman 2. Roman 2 requires us to find volume of oxygen produced. Volume of oxygen produced at RTP. At RTP, take note of that, at RTP. Proceeding, going directly to where I have my response, we shall have the following. So this is item 10, Roman 2. Item 10, Roman 2, volume of oxygen. So the item provides us with molecules of nitrogen dioxide. So we shall use molecules of nitrogen dioxide to find moles of nitrogen dioxide. Then from moles of nitrogen dioxide, we find moles of oxygen, then convert moles of oxygen to volume of oxygen. In this case, we are lucky. We are not going to go through all this because in item 1, we have already seen that moles of nitrogen dioxide, we have seen that moles of nitrogen dioxide are 48 moles. So you do not need to show the working again for moving from molecules to moles. We already have our moles, so we use them to find moles of oxygen. So we apply the concept of mole ratio. We are comparing what we have, nitrogen dioxide to oxygen, nitrogen dioxide to oxygen. From that equation, if you look at it carefully, you realize that for nitrogen dioxide, there is a 4 before. Then for oxygen, there is 1. So the reaction ratio is 4 to 1. If the reaction ratio is 4 to 1, then what of the 48? For 48, we shall have 1 over 4 times 48. And this gives us what? This gives us 12 moles of oxygen. 12 moles of oxygen. Now we convert these to volume of oxygen. To convert moles to volume of oxygen, you ask yourself, this volume is required at what? From the item, we have seen that this volume is required at RTP, and at RTP, 1 mole is equal to 24,000 centimeters cubed of oxygen. Then what of the 12 moles? 12 moles, this will be equal to 12 times 24,000. And in this case, we obtain 288,000 centimeters cubed of oxygen gas. So that is item 10, Roman 2. Then item 10, Roman 3, what does it require? Item 10, Roman 3 requires us to find what? So item 8, Roman 3 requires us to find the total number of atoms contained in the sample of lead to nitrate. Total number of atoms contained in the sample of lead to nitrate. So total number of atoms contained in the sample of lead to nitrate. So I go to where I have my response. This is the Roman 3. So for Roman 3, total number of atoms, we are provided with molecules of nitrogen dioxide. We convert those to moles, we convert them to moles of nitrogen dioxide, then from moles of nitrogen dioxide to moles of lead to nitrate, then to total number of atoms. So here they want total number of atoms. We are going to see how to find them. So note that 1 lead to nitrate. This is 1 lead to nitrate. 1 lead to nitrate has 1 lead. It has 1 PB. There is a bracket here and a 2 down here, implying that this 2 affects each and everything in this bracket. So we have 1 PB. If the 2 multiplies inside here, we have 2 nitrogens. Then 2 times 3, we have 3. 2 times 3, we have 6 oxygens. So we have 2 nitrogens and 2 times 3, which is 6 oxygens. So 1 lead to nitrate has what? Has 1 lead atom. It has 2 nitrogen atoms. It has 6 nitrogen atoms. So in this case, we are lucky. So if this is what we have, we are going to obtain atoms of lead atoms of nitrogen and atoms of oxygen. Then we shall sum them up to obtain the total number of atoms which are required by the item. So in this case, we are lucky moles of lead to nitrate. They have been calculated from item 1, and these were 24 moles. So I use these moles to find atoms of lead, atoms of nitrogen, and atoms of oxygen. So 1 mole of lead to nitrate, I start with atoms of lead. 1 mole of lead to nitrate has 1 mole of lead atoms. Then what of the 24 moles? The 24 moles will contain 1 times 24 moles of lead atoms. And in this case, we obtain 24 moles of lead atoms. These are moles of lead atoms. Then I convert them to atoms of lead atoms. I convert them to atoms of lead. Yes, sorry. So 1 mole of lead atoms is equal to 6.02 times 10 to the power 23 atoms. Then what of the 24 moles? 24 moles will equal to 24 times 6.02 times 10 to the power 23 atoms. And in this case, we obtain 1.44 times 10 to the power 25 atoms of lead. Those are atoms of lead. Now I proceed with atoms of atoms. We have seen that 1 lead to nitrate has 1 lead atom, 2 nitrogen atoms, 6 oxygen atoms. So in this case, the moles of lead to nitrate are already provided. We have calculated them. They are 24. So 1 mole of lead to nitrate has 2 moles of nitrogen atoms. Then what of the 24 moles? What of the 24 moles of lead to nitrate? These contain 2 times 24. And as a result, here I obtain 48 moles of nitrogen atoms. Then I find the actual atoms of nitrogen using Avogadro's relation. 1 mole of nitrogen atoms is equal to 6.02 times 10 power 23 atoms. What of the 48 moles? 48 moles, we shall have 48 times 6.02 times 10 power 23 atoms. And in this case, I obtain 2.89 times 10 power 25 atoms of nitrogen. These are atoms of nitrogen. We have calculated atoms of lead, now atoms of nitrogen. Next, atoms of oxygen. For atoms of oxygen, the moles of lead to nitrate are still 24, and 1 mole of lead to nitrate has 6 moles of oxygen atoms. Then 24 moles, we shall have 6 times 24. And here we obtain 144 moles of oxygen atoms. 144 moles of oxygen atoms, then we find the actual number of oxygen atoms using the Avogadro's relation. 1 mole of oxygen atoms is equal to 6.02 times 10 power 23 atoms. Then what of the 144 moles? The 144 moles we multiply with the Avogadro's number. And in this case, we obtain 8.67 times 10 power 25 atoms of oxygen. As a result, the total number of atoms are equal to the atoms of lead plus atoms of nitrogen plus atoms of oxygen. And in this case, we obtain 13 times 10 power 25 atoms, the total number of atoms of lead, the atoms that are present in lead to nitrate. So I would implore you to enjoy this day, because this day has been it is the day that the Lord has made. So we have to rejoice and be glad in it.